How strong is the filament made directly from the PET bottles? Welcome to my tech farm. A few weeks ago we had a meeting, Hungarian tech YouTubers, and there I met Walter, my colleague, very popular Hungarian YouTuber, and in one of his videos he recycled these PET bottles and made these sample filaments. And he gave me two samples to print some test specimens and to measure their strength. The method he used is based on Recreator 3D. That's an open source project. You need to print some parts, and some elements are from the old Ender 3, and basically this is a DIY project anybody can do at home. This video and the whole channel is sponsored by Polymaker, and if you still need some good PET filament, maybe you can try their glass fiber version. I will place the link down in the description to Recreator 3D, but also to his video. It's in Hungarian, but maybe you can enable the subtitles. And from one bottle he can make approximately 8 meters of filament. Now the method is based that these PET bottles are cut into the flat tapes, and then this flat tape is pulled through 1.75mm nozzle to make these sample filaments. But with this method it will not be solid inside, but it's twisted more like a pipe because it is hollow inside. And this means I have to increase the flow rate by 30%. Or the extrusion multiplier to 1.3. My problem is that approximately is not really enough for testing the strength, because just a little underextrusion and the part will be significantly weaker. I know the method how to check this correctly, but not with 8 meter sample filaments. Actually, if I increase the extrusion multiplier, it's not 8, but let's say 6 meters or something like that. One of the methods is to print some test objects from PETG, which is familiar, and from this PET, and to measure their weight. The density is not same, but it can be calculated. For the PET it is approximately 1.4, for PETG 1.25 kilograms per liter is the density, and for this it can be calculated. The second method is to print something in vase mode and to measure the thickness of the walls. Less accurate, but this can be also used to calculate the correct extrusion. All test objects are solid inside, printed with maximum number of the walls. Generic PETG is the star profile, but of course it's modified. 260 the nozzle temperature, 85 will be on the textured PEI, 8 the maximal flow, and of course very important is 1.3 the flow ratio, that's the extrusion multiplier, and I'm reducing the particle length between 30 and 50%. And with this I will need almost 5 meters of filament. I think it's loaded.
Just in case, I will add some glue.
It started, the first layer looks good. Let's see the bed adhesion. Oh, it will be good. And I don't worry that it will be too good because I used the glue on the surface. The printing looks nice, but it's a little bit hard to handle this filament because it falls down from the spool holder. But it will be fine. It's only 6 meters now. The printing looks very nice. I was very careful with this first printing to have enough filament, but probably I will print one for the impact test too, and maybe a few more test objects for the layer adhesion. I will try to print with the high temperatures too. It's finished a few seconds ago, and I have the feeling that the bed adhesion is good until it's hot. Yes, I have to wait until it cools down. Let it cool down completely. The printing is really nice, but look at this transition here. I hope it's visible on the camera too. And I think the reason for this is that it slowed down significantly after 5 millimeters. I still have approximately 2 meters of filament, and I want to print the test objects for the impact and for the temperature test. Oh, not good, because it requires almost 3 meters of filament. Okay. With this only impact test, and with the other color, the temperature test. It will be finished soon. This is the last layer, and I still have approximately 1 meter of filament, so I think I'll print some layer adhesion test objects on 275 degrees Celsius. This printing looks nice too, and it's printed on 275 degrees Celsius. Now I noticed some stringing appeared. The previous printing was completely clean.
And now let's print something with the transparent filament. Maybe. And finally, success. The filament is changed, but I could hear the popping sound, so maybe this one is not so dry like previous one. The printing is completely fine, and that popping sound disappeared very quickly. Maybe it was only on the edge of the filament because it's hollow inside, I'm not sure. And this is my solution for the filament. It's really hard to use the spool holder. It will be finished soon. But looks like from this sample I have more because I still have 6 meters, and maybe I can print the rest of the test objects so I will have a full set, and I can add that line to the pattern summary table. For the moment I was too optimistic, so even with this significantly reduced number of the test object, it requires more than 6 meters. Unfortunately I have to stop this printing. It's printing in the air. Must be some difference in the diameter or something like that, unfortunately. Looks like the failure is because on this part the diameter is much smaller, because I checked earlier it was fine, but this one is 1.55 millimeters approximately. That's too small. And this is the outer diameter. And on this part, if I just extrude it, it's not moving, only if I push it with my hand. I hope I will have enough for at least the temperature test object. Looks like on this part it will be better. It is 1.72 millimeters approximately. So this half meters has to be dropped out. And looks like the diameter stabilized now after that cut and out part. And it will be finished soon. I have enough filament for one last printing in the vase mode. I want to check how transparent is this filament and also how constant is the extrusion. Well, we can notice two things. It is relatively transparent, but from these horizontal lines we can see that the extrusion is not too constant. Only for this comparison I will print few test objects from this Bambu Lab PETG Translucent. I'm using the same file for this printing, of course with the different print settings. Few more test objects for the comparison. Actually I have a spool of regular PET from eSun, and I will print few test objects just for better comparison. I'm using the same print settings like in that review video of this material, and I'm using this black old texture PI sheet which I got with the P1P, because it's much better for this kind of materials. I don't even have to use the glue, it will not stick too much to it. Interesting, I can see some difference in the print quality in the function of speed with these vertical objects. And the last group is finished too. Quickly to check the weight. 1.244. 1.657. Heavier. 1.707. 1.811. Let's quickly measure the hooks. 2.087, 2.715, 2.813, 2.998. It's quite obvious that there is some underextrusion with the transparent PET because it's much lighter compared to the green version, but this is light too compared to the PETG because the density of the PET is much bigger compared to the PETG, so I believe that this is underextruded too, and this will be visible on the tests too. Tensile test horizontal printed objects. On the left side you can follow the comparison numbers. As expected, the transparent PET is very weak, but even the green version is weak too compared to the PETG. eSun PET. This number is very similar to the measured value in the review video of this filament. This means that we can still expect some higher values for the recycled PET if the print settings and extrusion is set correctly. Layer adhesion, vertically printed specimens. Okay, let's start. So the transparent PET is the weakest because of that big underextrusion. Then this is the green version printed on 260 degrees Celsius, and looks like printed on 275 is weaker, but actually it is the average from two. One is strong and the other is very weak, and that's because of that stringing. I'll explain it soon. With the stringing we have maybe just one weak layer, and like a weak chain it will have a weak layer adhesion in the test. And the strongest is the PETG. And then eSun PET. This is a little bit weaker compared to that review video, but in the review video I didn't have the stringing, and I have it now. And let me explain you why is this important for the layer adhesion. The stringing is oozing from the nozzle, but the head is moving from one location to other. The oozing is lost material, but it will not be compensated with the extrusion. So that material you see in the stringing should be part of the printed object. That's why stringing, because of the wet filament or too high temperature, may result weaker layer adhesion. Hooks side by side all four. And again, two recycled PET filaments are much weaker in this case compared to the PETG or eSun PET, and a main reason for this is not the material property but the underextrusion during the printing. This results not only weak layer but also the wall adhesion, which is important in this case. And this is how healthy break should look like with these hooks. 3-point bending test. These are recycled PET filaments. Translucent PETG and eSun PET speed up 8 times. Max load, bending strength and elastic modulus, but I will show you soon everything on the graph. And here we can see how weak is this layer and wall adhesion with the recycled PET filaments. The bending strength is calculated from the maximal load, and far the weakest is the transparent PET. Other three more or less similar. Of course the strongest is the eSun PET. Now with the elastic modulus, nothing unusual with these three, but with the transparent PET, could be the reason for this higher value is that the points which I use for the definition of that slope is out of that linearity, and that's why it gives us the highest result. So I will take this number with higher restriction, but unfortunately I don't have the picture of the graph anymore. IZOD impact test side by side all three. Not really typical break in this test, result of the weaker wall adhesion. And the results, but let's see them on the graph. These two are very brittle materials, but look at this green PET. Look like very tough material, better even than ABS. But if you are following my channel, then probably you already know the reason for this, because I mentioned several times when I find the material with a weaker layer adhesion, it usually performs good on the impact test. It is something like a leaf spring effect, and that's what we can see here. Temperature test in the oven. I want to record the temperature of the first deformation, and PET started to deform quite early, like PETG, and the PET was the best in this case. With the PET, annealing could help with the temperature resistance, and at this point they are very similar to each other. But again, reminder, this transparent PET was printed with big underextrusion.
Our first thought may be that this recycled PET is quite weak, but it's not. I already saw other videos too, and the main reason for this weakness is actually the underextrusion, which I mentioned several times, which is a result of this dimensional inaccuracy. And this shows the weakest point of this Recreator 3D, that we put a lot of work and then we get 8 meters of sample filament, and maybe we don't even know that it is dimensional inaccurate, and we print some mechanical parts and it will be weaker. And actually when I printed those green test objects, they look perfect. I didn't even know that they are weaker until I didn't measure them. Then I know that it's underextruded. So this is a danger in these recycled materials, that we print something and maybe we don't even know that it is much weaker. Actually it is unstable, so we don't know what to expect here. That's why I think that this Recreator 3D don't have too long future as it is now. I hope the Creality's new filament recycling kit will work nice. Probably Creality will not send it to me. I didn't talk too nice about some printers, and since that Creality don't send me the products. Few dryers or something like that which I got was from the geek buying. But never mind, if I think that it's worth it, then maybe I will buy it. But I still think the best solution would be if manufacturers would collect these PET bottles and they would recycle it and make filaments from it. Okay, huge thanks to the Walter for sending me these sample filaments, huge thanks to the Polymaker for sponsoring my channel, and to all my Patreon supporters, and all them together makes this kind of videos possible. And to all you others, well, thank you for watching this video to the end, and as always, happy printing!